Welcome to the structure analysis course. So in the last two classes before we have started the new module, that is energy method of calculating the slopes and deflections in a structure. So in the last class we have discussed the Castigliano's theorem to find out the slopes and deflections using this method. So we saw this energy method is very much useful when we have the multiple loads are acting on a structure. So for example, if a structure, so let me just draw it. So here is a simply supported beam. One hand is hinge, another hand is roller. So if a single load is acting, maybe point load, or maybe UDL is also acting, maybe half of the UDL is also acting. So this type of UDLs, or that point loads, if it is acting, then it is a simple loading condition actually. So using this geometric method, we can easily solve it. Just drawing the bending moment diagram and M by EI diagram, we discussed three methods to calculate the slopes and deflections using the geometric method of structure analysis. But if many loads are acting at a time, maybe a UDL or UVL, uniformly varying load, or multiple point loads are acting on a structure. So in that case, if we employ the geometric methods, then the drawing of bending moment diagram and share for that M by EI diagram will be little bit hectic. So to overcome this difficulty, the energy method is very much useful in that case. So when we have the very complex loads are acting on a structure, so that's we discussed the conjugate that Castigliano's theorem method, how to solve it. So basically Castigliano's theorem is nothing but the partial derivative of a total strain energy in a beam with respect to the load at that point will give us the displacement at that point. So it is very simple method, and just we have to write the equation of the strain energy in a beam, and then if we take the derivative we will get the slopes and deflections. So now that method, Castigliano's theorem method, is only applicable for the determinant structure. So even for the earlier methods what we discussed, it is geometric methods that are also usable for the determinant structure. Determinant structure means all the unknown reactions are equal to the number of equilibrium equations, right? So this structure, if you this is a determinant structure. How? Because here this is a hinge support means we have the two unknown reactions, and this is roller support. You have here one single unknown reaction, so total three unknown reactions, and we have the three equilibrium equations to solve, like summation of all horizontal forces equal to 0, summation of all vertical forces equal to 0, and summation of all moment about a particular point should be equal to 0. So we have three equations, three unknowns, so we can get it, we can solve all the unknown reactions in this beam. So this beam is a determinant beam. Even whatever problems till now we have solved, all problems are actually a determinant beam. Even we discussed cantilever beams also. Cantilever beam means there also you will find it is a determinant structure. So cantilever beam means one hand is fixed, another hand is free, and maybe some loads are acting, whatever may be the typing of load. So here you have the fixed end means we have three unknown reactions. So horizontal, vertical, and a moment. So three unknown reactions we have. So even we discussed different types of beams. Till now we solved many problems. So all problems are basically determinant structure, means the number of unknown reactions are equal to the number of equilibrium equations. But if you look into the real structures, whatever structures we are standing, we are going to mall, shopping malls, cinema halls, everywhere, if you see that structures are not actually a determinant structure, these are indeterminate structure. So we have more unknowns compared to the equilibrium of equations. So when you solve the real structure, then whatever method we discussed till now, that method may not be applicable in that case, because the real structure's maximum case, it is an indeterminate structure. Maybe in that frame structure, the all ends may be fixed end. So in that case, the so much undeterminacy will become indeterminacy will become into the structure. So in this method, today we'll discuss how to solve the indeterminate structure, how to get the reaction force. For example, if I draw a simply supported beam with one hand hinge, and this end is also hinge. So in that case, here you have two unknown reactions, one vertical, one horizontal. Similarly, here also we have one vertical, one horizontal. So total we have four unknown reactions, 1, 2, 3, and we have 4. So total 4 unknown reactions are there. So, and we have only 3 equilibrium of equations, that is summation of all horizontal forces equal to 0, summation of all vertical forces equal to 0, and summation of all moment about particular point equal to 0. So we have 3 equations, but we have 4 unknowns. So basically we can't solve using, we can't get the values of all the reactions within simply the equilibrium of equation. So that's what, in that case, we have to use this method, that is theorem of least work method, to calculate the reaction in the other forces also. So 3 values we can get it using these 3 values, but one will be unknown, that we can't get it. So that can be solved using the theorem of least work. So let's get started. So the principle according to this theorem is the partial derivative of the strain energy of a statically indeterminate structure. So please note here we are discussing about the statically indeterminate structure. But till now all the structures what we discussed was statically determinate. Means number of reactions are equal to the number of equilibrium equations. So but here we are talking about the statically indeterminate structure with respect to the statically indeterminate action would should vanish as it is the function of such redundant force to prevent any displacement at its point of application. So let's elaborate it in more details, principles of theorem of least work. So this is beam, if you consider, so this beam is an indeterminate beam with a order of 1. How? So this end, this left hand B end is nothing but a fixed end. So we have 3 reactions, some horizontal, vertical, and you have a moment. So we have here 3, and here at this end we have 1. So total 4 reactions are there, and we have only 3 equilibrium equations. So this beam is a propped cantilever. So it is a cantilever, and which this end is propped, right, supported. So basically this beam is an indeterminate beam with a degree of 1. Why? Because here we have 3 unknowns, 3 reactions, and this is roller support, so we have 1 reactions. So total 4 reactions are there, and we have only 3 equilibrium of equations. So we can't get all the equations, we can't get all the values using the equilibrium of equation. So in this problem we'll solve using the theorem of least work. So let's consider a beam. So this is a propped cantilever, which is actually indeterminate beam, and multiple loads are acting, P1, P2, P3, Pn dot dot, many loads may be acting. So because of application of the load, the beam will deflect. So this is a deflected shape of a beam. So now in this method, first we have to make our structure a determinate structure. How? This is the indeterminate for structure, so we have to remove one or more support. So in this case it is only one support if we remove. So we have 4 unknowns and we have 3 equilibrium of equation, right? So if we remove one support, then we can make it the beam as a statically determinate beam. So our first job will be to find out which force or how many force shall we remove to get the determinate beam. So here it is one force, if we remove we will get the determinate beam. So now so the forces which will be removed, or the reactions which will be removed, that we call it redundant force. So that's what in the principle, if you say redundant force, redundant force is nothing but the force which will remove, the reaction will remove to make the structure a determinate structure. So this is the structure. Now here if we remove this support itself, so this propped support, this entire right hand side a support, if we remove, then it's simply a cantilever beam where one end is fixed, another end is free. So here we consider, let's consider this a is a ra, what is vertical reaction, that is as a redundant force. So now we got two structure. Okay, so one is with this redundant force, one is with this force. So just remove this support. So what we'll get? We'll get a cantilever beam with a P1, P2, P3, dot P, and all the forces are acting. So this is our first part. So if you see this beam, so this is a cantilever beam with only P1, P2, P3, Pn, all the loads are acting, but there is no support at a and is free. So this is our first part. So we divided this entire beam, original beam, into two parts. One is we removed this part, removed this support itself, that is reaction ra we removed, and we made this beam propped cantilever into a cantilever beam. So this is a cantilever beam with the multiple loads are acting. And next part we divided only a cantilever beam with only forces are acting, only ra reaction is acting, redundant force is acting. So this is another this is another beam where there no force is acting, but only redundant force is acting, ra. So this is reaction force, right? Ra. So only Ra is acting in a beam. There is no force. So basically, what we did with this entire structure, we divided into two parts. One is, first part is this cantilever beam with all the forces, which is nothing but this figure, plus a cantilever beam with only redundant force Ra, that is reaction force Ra. So now, if we superimpose both, we will get our final beam. So we have to apply the method of superposition also to get the final structure. So final beam we divide into two parts, and we made two statically determinate beams. So this beam is also statically determinate, and this beam also statically determinate. But if you combine, if you superimpose both the beams, we will get our original beam, that is this one. So basically, we have to make our original beam or indeterminate beam into a multiple determinate beams. So here it was only one force. If we remove, we get determinate beam. That's why we divided it into two parts. But in other case, or in real structure, so maybe you have to remove multiple for redundant forces to get the determinate beam. So in that case, maybe three, four beams we have to add. Then only we'll get our final original beam. So that is our basic principle. So let's prove the derivation. So already we saw this is the energy work done by the external force, as we discussed. So total energy, we call it capital U, is equal to half into total P. Let me just draw it quickly, the beam. So we are talking about a cantilever beam, so which one end is fixed, and we have multiple P1 and then P2 dot dot, multiple loads are acting, and you have Pn. And because of this, so this is deflection happened. So deflection here it is u1, deflection here it is u2, deflection here it is un. So this is our main original figure. So the total strain energy due to this P1, P2, Pn will be what? Half into force into that base into that, half into force into work done. Total work done will be half into force into displacement. So force is P1 into U1. So this is first part, plus because of the second load, how much it will be? Half into P2 into U2. Like that, all the forces we have to act. So what we'll do is we'll find it out how much deflection happened at this end. So we divided our main original beam into two parts. One was this cantilever beam with only loads are acting, and next part we divided was only the cantilever beam with a redundant force acting. So on next part was, this is first part. So this is first, and second was only redundant forces acting, that is Ra. So because of Ra, the deflection will be something like that. Something like the deflection will be happening. So this is our second part. So our real beam, if we superimpose 1 and 2, then we get our real beam. So now we have to find out how much deflection happened here at the end A. So how will you do it? We can simply employ, because these are two determinate beam. Original beam was indeterminate, we made it into a determinate beam. So now we can employ the Castigliano's theorem or any geometric method what we discussed in the earlier. We can employ and we can find out what is the deflection happened here or here, any place. Okay, so let's employ the Castigliano's theorem to find it out how much deflection happened at this end. So that's what we have calculated the total strain energy because of all the loads P1, P2, P3, Pn. So this is total strain energy developed. So as we are finding out the displacement at this point A, so this is our A point, final tip of this being A. So here we are finding out what is the displacement happened. So, but as per the Castigliano's theorem, if so whatever total strain energy will be there, we have to derive it with respect to the force acting at that point. So that is the Castigliano's theorem. So total strain energy has to be derived with respect to the force at that point. At that point means at A, but at A there is no force is acting, right? Zero force in the question, there is not given. So A is zero force. So we have to apply a fixed TCS force, imaginary force of Q. So let's apply imaginary force Q at end A, because we are finding out displacement UA. Okay, so now total strain energy will be half into this entire term. Last part, if you see, half into Q into A also came, because Q we added a imaginary force, and the displacement at under A is UA. So this is our total strain energy. Now we know what is U1. U1 is a U1 means displacement under the load P1. So so all the loads will be contributing the displacement at U1, right? So whatever U1 happened displacement, that is not only because of P1, but all the loads are acting together. That's why we got final displacement, that is U1. So U1 can be written as in this form. We discussed in the last classes how we derived. So where A11, A12, these are all the flexibility constants. So this is our U1. Similarly, U2 also can be written, U3 also can be written with the flexibility constants. So now you substitute U1, U2, U2's value in the original US equation. So this is our original US equation, half into P1 into U1. So U1's value, this is the entire part of U1. We replaced it with U1, this one. Similarly, half into P2 into U2, half into P2 into U2. This entire part is U2. Like that, all the values we substitute in our US equation. Now, as per the Castigliano's theorem, total strain energy is US. So that strain energy, if we do the partial derivative with respect to the force at that point, then we will get the displacement at that point. So the force at that point is Q, nothing but Q. So that the entire strain energy we have to divide, we have to take the derivative with respect to Q. So Q will be, so just if you take the derivative, so you, this is the final expression you will get it. If you derive this expression with respect to Q, so basically, without Q, all the term will simply vanish. And remaining part, whatever is there, that we have written here. So for example, from this portion, half into P1 into P1 square A11, if you multiply this portion with this with this, like that all multiplication happens. So in every place it is constant, right? So everything will go. Wherever Q is there, that will be, that term will be there. So for example, if you multiply this term with this, then half into P1 into A1 A Q. So Q will simply go, so A1 P1 will be remain. So half anyway from that side also will come another value. So half it will be 1. So this is our final expression. If you just do it all the calculations, then you will get this is our final expression for the displacement at that point. So this is nothing but UA. So UA is this is same displacement here. So because Q is a fictitious force, right? Q is originally the in real beam Q was not there. We added imaginarily Q. So that's why if you substitute the Q equal to 0 in this expression, what you get is final UA, which is nothing but this is the entire part. So this last part will go away because Q is 0. So this is our final expression. Now similarly, now come to second beam. So this beam, second beam, here we are applying a force RA. Only redundant force is applied. There is no P1 P2 in this beam. So what we did, original beam, if you still recall last slide, original beam we divided into two parts. One was this cantilever beam, another was this and second cantilever beam. If you add both, then we will get our original beam. So only only RA is acting in this cantilever beam. So how much will be the total strain energy? We know already, we derived this expression RA. If a single force is acting tip load, then that much RA, that strain energy will be developed into a beam. Now if we derive this strain energy with respect to RA, because we are finding out what is the displacement happened at this point A. So if you take the derivative as per the Castigliano's theorem, if you take derivative with respect to Ra, this expression you will get, this is our final expression. So this is the UA in the second figure, that is in the, if we apply a redundant force, how much displacement takes place here, that is UA, which is the value is this much. So now if you see in the real beam, let me draw the real beam also. So real beam will be a cantilever, a fixed end. This end is fixed end, and we have multiple loads acting. P1, P2, many loads are here, and then at the end Pn, and then here we have a support. So the roller support. So this was our original beam. So this original beam is nothing but divided into two parts, as we discussed, this part 1 and part 2. So what is part 1? Part 1 is nothing but there we removed this support and we made this beam into a determinant beam. So this is our part 1, and part 2 is we removed all the force, only the reaction force is acting, that Ra. This is part 2. So if you superimpose both, you will get our original beam. So if you see in the real beam at this point A, This is A point. So what is the displacement? So in imagine, so we when we divided, there was no support, so that's why deflection is allowed here. Here also we applied only redundant force, so deflection is there. But in the real beam, if you see real beam at this point, what is the deflection? It is zero, right? Because here its support is there, whatever loads are acting. So if you draw the diagram, that is, this is a bending diagram. So displacement at this point A is nothing but zero, because here we have support. But if you see in the first diagram, because there is no support, there will be deflection. And similarly here also, there is no support, so that's why uh, the deflection will be happening here, RA. So whatever deflection you computed, UA. But in real beam, the deflection at this point is zero. So whatever RA we computed from this figure, so whatever displacement is this part, and whatever displacement is this part, this should be, if you add both, it should be zero, because our original beam, it is zero. There is no displacement. So whatever you got displacement from the figure one, so this is figure one's, that figure one's displacement UA, we got this one. So this value must be equal to whatever we got this UA from this figure. Then only we'll get the zero displacement at A. We want displacement should be zero at A. So that's why del US del Q, this is equal to UA, equal to nothing but this value opposite minus of this. That's why if you add both, you will get zero. So this plus this, if you do it, then you will get the zero. Whereas here the displacement is zero. So now from this expression, if you move this portion into this side, you will get del del r equal to us plus ur. So here del q and del r. So what is q? Q was also imaginary load acting on it. So we can conveniently replace q with ra. So just q, if you replace it with ra, because at point A only we added a q as imaginary force. So if you replace q with ra, and this is our final expression we got. So US plus UR equal to 0. So US plus UR is US is strain energy because of P1, P2, P3, and UR is the strain energy because of only RA. But in the real structure, both are acting together, right? So total strain energy will be strain energy because of P1, P2, P3, that is US plus UR. So US plus UR is the total strain energy of the structure U delta equal to RA. So that is our this theorem, that is principle of virtual work theorem. So there, if you take derivative of strain energy with respect to the redundant force, we will get zero. So that is our principle, the theorem of this theorem of virtual work. That is, virtually we worked, we applied some load, and whatever redundant force is there, if you take the derivative with respect to redundant force, you should get zero. So this is the proof of this equation. So let's solve a problem quickly to understand the method more in details. So find the reaction force at a propped cantilever. So this is a propped cantilever given to us. Just now we saw propped cantilever is an indeterminate beam, where here you have three unknowns and here you have one unknown. So total four unknowns are there. So it is a 1 degree of indeterminate beam. So find out the reaction propped shown in figure. Assume that flexural rigidity EI is a constant throughout. So you have to find it out, the reactions, all reactions. So here you have three reactions, here you have one reaction. So all the four reactions values you have to find it out. So this is an indeterminate beam with an order of 1. So again we have to make our beam into a two determinate beam. So this is first beam, first part, that is we removed RA. So and only force is acting. So to what is the total strain energy? We know, and this total strain energy in this beam will be integration 0 to L m square by 2EI by dx. So we derived this expression. We know the total strain energy because of this UDL will be that much. So according to the least square theorem, so here which one is the redundant force? Redundant force is which moved this portion RA. RA we removed and we made our beam a determinate beam. So our redundant force is RA. So as per the theorem of least work method, just now what we discussed, that is total strain energy. If you take the partial derivative of total strain energy with respect to the redundant force, the value should be equal to 0. That's what we derived in the last slide. Theorem of least work. Uh, but just substitute, so du dx by rb. So u already we know, this is the expression. So just substitute it, m by ei. If you just substitute all the values, you will get this is the final expression. So now bending moment, so this expression basically you have to derive it with respect to rb, so you will get this is the expression. and this should be equal to 0 as per the theorem of least work. So now what is the bending moment at a distance of x from B? So let's take a section here. So here already a section is there, so which is at a distance of x from the from the load here. Then how much is the moment at this point section? So moment will be, because of RB, we have RB into X, which is, anti-clockwise. That's why the positive sign. Minus, you have the UDL is also acting. So UDL. UDL is acting downward. So that is what is the total UDL? W into X into distance is X by 2. This is a total moment at a distance of X from the right hand side. So from here at here, this is the moment M. So now if you substitute dm, so moment value, if you substitute this moment value here, what will you get? And this is the expression. If you derive it with respect to RB, del m by RB, what will you get? So this term will be RB with respect to RB, so you will get X. So here it is constant, so only you will get RB. So del m by del RB equal to X. So now substitute this entire part, del m by del x. So here del m by del x is also there. Substitute it with x. So what do you get? Final expression. So del u by L b equal to integration. Substitute what is the moment value. Moment value is this much. So we have written moment value this much by ei into del m del x is nothing but x. So that's what we replaced. This x we replaced here into dx. Now take the derivative. What will you get? So take the integration and you find it out. What is just integration 0 to L with respect to dx, then we get RA and RB both. So from this expression, now if you take integration, so this expression, this term equal to 0, from here easily we can compute what is the value of RB. So once we know RB, so we got RB this much. So now total RB you know, so RA will be what? Total load minus RB will be RA. So total load is WL minus RB will be RA over, and simply now moment MA also can be determined at this point. Just substitute RB value also we know, so we can find out what is the moment at A. So now all the reactions now we computed using the moment theorem of least work. So we have divided this entire beam into two parts. We removed this support. First one is this beam, and next one is only with this. We applied the theorem of least work, and then we computed RA, RB, and MA. All the reaction force we computed using this method. So this method is very much useful when we have the indeterminate structure. And if you look into, in reality, all the structures are basically indeterminate in nature. So this method is very much useful in that case to solve all the reactions, support reactions into a structure. Thank you so much.